Now, let's move on to the next topic of our chapter, that is complement of a set. Let U be the universal set and A be the subset of U. Then, the complement of A is the set of all elements of U which are not the elements of A. The complement of A can be denoted by writing A dash, and that is set of all x such that x belongs to U and x does not belongs to A. So, here the elements belongs to the universal set but does not belong to A. So, using the difference operation, we can write A complement is equal to U minus A. Let us understand this with the help of an example. Let U equal to set 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 and A equal to set 1, 3, 5, 7 and 9. Find A complement. Here, the universal set U and the set A are given and we have to find out A complement. So, here A complement will be the set of all the elements of U which are not in A. So, what are those elements? We can see that they are 2, 4, 6, 8 and 10, and we can write this as A complement is equal to U minus A, which is equal to set 2, 4, 6, 8 and 10. Here we can see that A complement is also a subset of U, as all the elements of A complement is also in U. So we can say that if A is a subset of the universal set U, then its complement A complement is also a subset of U. Now what if we need to find the complement of A complement? That is A complement the whole complement. Let us consider our last example. Here A complement is equal to set 2, 4, 6, 8 and 10. Then what will be A complement the whole complement? It will be the set of elements which belong to the universal set U but does not belongs to A complement. So, what are those elements? We can see that they are 1, 3, 5, 7 and 9. So, we can write A complement the whole complement is equal to set 1, 3, 5, 7 and 9, which is nothing but set A. So we can say that A complement the whole complement is equal to A. A complement the whole complement can be symbolically written as set of all x such that x belongs to U and x does not belongs to A complement. The complement of a set A can be shown using a Venn diagram. Here, the circle represents the set A and the shaded region around it represents the elements that belongs to U but does not belongs to A, and that is A complement. Now, let's take a look at another example. Let U be the universal set of all the students of class 11 of a co-educational school and A be the set of all girls in class 11. Find A complement. This is a tricky question. Here, the universal set U consists of all the students of class 11 and set A consists of all the girls in class 11. So, think about it. What will be the complement of A? Let's take a look at it with the help of a Venn diagram. Here, the universal set U includes all the girls and all the boys of class 11, and set A contains all the girls of class 11. We know that the complement of A will contain all the elements which belongs to U but does not belongs to A. So clearly, the set of all the boys of class 11 will be the complement of A. Now, let's move on to the next example. let U is equal to set 1, 2, 3, 4, 5 and 6 and A equal to set 2 and 3 and B is equal to set 3, 4 and 5. Find A complement, B complement, A complement intersection B complement, A union B, and hence show that A union B whole complement is equal to A complement intersection B complement. First, let's find out A complement. We know that A complement is equal to U minus A, and that is set of elements which belongs to U but does not belongs to A. So, A complement is equal to set 1, 4, 5 and 6. Next, let's find out B complement. B complement is equal to U minus B, that is set of all the elements which belongs to U but does not belongs to B, and that is set of 1, 2 and 6. Now we have to find out A complement intersection B complement. It will be the set of elements common to A complement and B complement. So what are those elements? We can see that 1 and 6 are the common elements. So we can write A complement intersection B complement is equal to set 1 and 6. Now let's find out A union B. A union B is the set of all the elements of A and all the elements of B, that is set 2, 3, 4 and 5. From this we can find out A union B complement. This set will contain elements that belongs to U but does not belongs to A union B, and they are 1 and 6. So A union B whole complement is equal to set 1 and 6. This is the same as A complement intersection B complement. From this we can say that A complement intersection B complement is equal to A union B whole complement. This result is true in general. If A and B are any two subsets of the universal set U, then A complement intersection B complement is equal to A union B whole complement. Similarly, A complement union B complement is equal to A intersection B whole complement. We can state this as the complement of the union of two sets is the intersection of their complements, and the complement of the intersection of two sets is the union of their complements. And these are called the De Morgan's laws. Now let's take a look at some properties of complement sets. First one is complement laws. They are A union A complement is equal to universal set. Second one, A intersection A complement is equal to 5. Let's understand this with the help of an example. Consider the sets universal set, set 1, 2, 3, 4, 5 and 6, and A equal to set 3 and 6. Here A complement is equal to U minus A, and that is the set of elements which belongs to U but does not belongs to A, and that is set 1, 2, 4 and 5. So A union A complement will be the set of all the elements of A and all the elements of A complement, and that is set 1, 2, 3, 4, 5 and 6. We can see that this set is equal to the universal set. Similarly, A intersection A complement will be the set of all the elements which are common to both A and A complement. Here we can see that there are no common elements, so this will be an empty set. From this we can say that both these laws are true. Next one is De Morgan's laws, the one that we saw previously. That is A union B whole complement is equal to A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. The third one is law of double complementation. That is, A complement whole complement is equal to A. Next one is the law of empty set and universal set, and that is phi complement is equal to U and U complement is equal to phi. Let's look at an example. Consider the universal set 1, 2, 3 and 4 and phi, which is the empty set. Here, phi complement will be the set of elements which belongs to U but not to phi, and they are set 1, 2, 3 and 4, which is the same as the universal set. And since U contains all the elements, U complement will be a null set, which is equal to phi. So this law is also true. Now let's move on to the next topic of our chapter, that is practical problems on union and intersection of two sets. By now we have become familiar with union, intersection and difference of two sets. In this section, we will be using them to solve some practical problems, and we are going to use the following formulas to do so. First one, number of elements in union of disjoint sets. If A and B are two finite sets where A intersection B is equal to phi, then n of A union B is equal to n of A plus n of B. In simpler words, if A and B are finite sets and these sets are disjoint, that is A intersection B is equal to phi, then the number of elements of the union of the sets A and B is equal to the sum of the number of elements in set A and set B. Second one is number of elements in union of two sets. If A and B are two finite sets, then n of A union B is equal to n of A plus n of B minus n of A intersection B. To put it simply, the number of elements in the union of sets A and B is equal to the sum of the number of elements of the sets A and B minus that of their intersection. We can also write this as n of A minus B plus n of B minus A plus n of A intersection B, because A union B can also be expressed as the sum of three disjoint sets, that is A minus B, B minus A and A intersection B. The third one is number of elements in union of three sets. If A, B and C are three finite sets, then n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. We can observe from the Venn diagram that the union of the three sets will be the sum of the number of elements of set A, set B, set C and the common elements of the three sets excluding the common elements of sets taken in pairs of 2. Now let's take a look at some examples and solve them using the formulas that we just discussed. First one, if X and Y are two sets such that X union Y has 50 elements, X has 28 elements and Y has 32 elements, how many elements does X intersection Y have? First, let's write down the given data. It's given n of X union Y is equal to 50, n of X is equal to 28, n of Y is equal to 32, and we have to find out n of X intersection Y. Now, looking at the data, what is the formula that can be used here? Yes, we can use the formula for finding the number of elements in the union of two sets. That is, n of A union B is equal to n of A plus n of B minus n of A intersection B. Here, instead of A and B, we will be using the sets given here, that is X and Y. Now, let us substitute the values in the formula. Then we get 50 is equal to 28 plus 32 minus n of X intersection Y. Now, taking n of X intersection Y to the LHS and 50 to the RHS, it becomes n of X intersection Y is equal to 28 plus 32 minus 50. Here, 28 plus 32 is 60 and 60 minus 50 is equal to 10. So, our final answer is n of X intersection Y is equal to 10. Now, let's move on to the next example. In a school, there are 20 teachers who teach mathematics or physics. Of these, 12 teach mathematics and 4 teach both physics and mathematics. How many teach physics? Here, let M denote the set of teachers who teach mathematics and let P denote the set of teachers who teach physics. In the question, the word OR indicates union and indicates intersection. So, here the number of teachers who teach mathematics or physics is equal to n of M union P, which is equal to 20. The number of teachers who teach mathematics is equal to n of M, which is equal to 12. The number of teachers who teach mathematics and physics is equal to n of M intersection P, which is equal to 4. From this data, we have to find the number of teachers who teach physics, and that is n of P. So, what is the formula that can be used here? The same one that we used in our last example. The formula to find the number of elements in the union of two sets. So here, the formula will be n of M union P is equal to n of M plus n of P minus n of M intersection P. On substituting the values, we get 20 is equal to 12 plus n of P minus 4. On solving this, we get n of P is equal to 20 minus 12 plus 4, which is equal to 12. Therefore, we can say 12 teachers teach physics. Now, let's move on to the next question. In a class of 35 students, 24 like to play cricket and 16 like to play football. Also, each student likes to play at least one of the two games. How many students like to play both cricket and football? Here, let C be the set of students who like to play cricket and let F be the set of students who like to play football. It's given number of students who like to play cricket is n of C, which is equal to 24. Number of students who like to play football is n of F, which is equal to 16. Number of students who like to play at least football and cricket. It's given that each student likes to play at least one of the two games. So this includes every student of the class, and that is n of C union F, which is equal to 35. Now, from this data, we have to find out the number of students who like to play both cricket and football. So this set will consist of students that are common to both C and F, and that is n of C intersection F. So again, we will be using the formula for finding the number of elements in the union of two sets, that is n of C union F, which is equal to n of C plus n of F minus n of C intersection F. On substituting the values, we get 35 is equal to 24 plus 16 minus n of C intersection F. And on solving this, we get n of C intersection F is equal to 24 plus 16 minus 35, which is equal to 40 minus 35, and that is 5. From this, we can say that 5 students like to play both cricket and football. Now, let's take a look at another example. In a survey of 400 students in a school, 100 were listed as taking apple juice, 150 as taking orange juice, and 75 were listed as taking both apple as well as orange juice. Find how many students were taking neither apple juice nor orange juice. Here, let A and O denote the set of students taking apple juice and orange juice respectively. It's given number of students who take apple juice, that is N of A is equal to 100. Number of students taking orange juice is N of O, which is equal to 150. Next one is number of students who take both apple juice and orange juice. Here, these students are the common elements of the set A and O, and that is N of A intersection O, which is equal to 75. With this data, we have to find out the number of students who neither take apple juice or orange juice. But first, we need to find the total number of students who drink either apple or orange juice, that is N of A union O, which is equal to N of A plus N of O minus N of A intersection O. Now let's substitute the values here. Then we get 100 plus 150 minus 75, and that is equal to 175. Here we have the total number of students who take either of the juice. So, by subtracting this value from the total number of students, we can find out the number of students who take neither apple juice nor orange juice, and that is 400 minus 175, which is equal to 225. Hence, 225 students take neither apple juice nor orange juice. Now, let's move on to the next example. There are 200 individuals with a skin disorder. 120 had been exposed to the chemical C1, 50 to chemical C2, and 30 to both the chemicals C1 and C2. Find the number of individuals exposed to first one, chemical C1 but not chemical C2. Second one, chemical C2 but not chemical C1. Third one, chemical C1 or chemical C2. So here there are 3 sets. U, which denotes the universal set consisting of individuals suffering from skin disorder. A, which denotes the set of individuals exposed to chemical C1, and B, which denotes the set of individuals exposed to chemical C2. It's given that number of individuals with skin disorder, which is N of U, is equal to 200. Number of individuals exposed to chemical C1, that is N of A, is equal to 120. Number of individuals exposed to chemical C2, and that is N of B, which is equal to 50. And number of individuals exposed to both the chemical C1 and C2, which is equal to N of A intersection B, is equal to 30. First, let's find the number of individuals exposed to chemical C1 but not chemical C2. Individuals exposed to chemical C1 will contain individuals exposed to only chemical C1 and individuals exposed to both chemical C1 and C2. So, number of individuals exposed to chemical C1 but not chemical C2 is equal to number of individuals exposed to chemical C1 minus number of individuals exposed to both chemical C1 and C2, and that is N of A minus N of A intersection B, which is equal to 120 minus 30, and that is equal to 90. Hence, the number of individuals exposed to chemical C1 but not C2 is 90. Next one is individuals exposed to chemical C2 but not C1. Individuals exposed to chemical C2 contains individuals exposed to only chemical C2 and individuals exposed to both chemical C1 and C2. So, number of individuals exposed to chemical C2 but not chemical C1 is equal to number of individuals exposed to chemical C2 minus number of individuals exposed to both chemical C1 and C2, and that is n of B minus n of A intersection B, which is equal to 50 minus 30, and that is equal to 20. Hence, the number of individuals exposed to chemical C2 but not chemical C1 is 20. Next, we have to find the number of individuals exposed to chemical C1 or chemical C2, that is n of A union B. So, how can we find this? Yes, we can use the formula for finding the number of elements in the union of two sets. That is, n of A union B is equal to n of A plus n of B minus n of A intersection B. On substituting the values, we get n of A union B is equal to 120 plus 50 minus 30, and that is equal to 140. Thus, the number of individuals exposed to chemical C1 or chemical C2 is 140.